All right, welcome back. This is lesson 3 on arithmetic sequences, and it's imperative before watching this lesson that you first watch the first 2 videos on arithmetic sequence, because in those 2 videos I go much more in depth introducing what a sequence is. Okay, but on the board I've put again our definition of a sequence, reminding you that a sequence is a function whose domain is a set of what? Natural numbers. Reminding you that the natural numbers are your counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth forever. But we're skipping a lot of numbers, okay? All numbers between 3 and 4 are skipped. For instance, 3.5 is not a natural number. 3.6 is not a natural number. 1.7 is not a natural number. There are no numbers between 1 and 2 in this set. There are no numbers between 2 and 3. These are very simple numbers. We're skipping numbers, and again, there are no negative numbers in the set of natural numbers. And there are also 0 is not a natural number, so it's positive counting numbers only. All right, now for the problem given, well, just very quickly, we're going to talk about arithmetic sequence. We're going to finish this up, and then we're going to start on geometric sequence in this lesson. But the problem given, this is page 692, number 22. I just want to address this homework problem for a couple reasons. Page 692, number 22 was assigned as homework. And let's look at what's given here. It says the height at 9 is 45 and the common difference is -3. Okay, remember, common difference is what is being added. Okay, so we're going to look at height at 9 is 45. Now let's go ahead and write this vertically. Height at 9 is 45, and we're going to first find height at 10. Now common difference is what is being added. Okay, what is being added? To go forward, to go to the next height, to go from height at 9 to height at 10, we add what? We add -3. So to go from height at 9 to height at 10, add -3 to 45, we get what? 42. And to find height at 11, do it again, add -3, and we get what? 42 plus -3 is 39. And so we see that the values are decreasing by 3. Adding -3 is the same concept as subtracting, but reminding you with arithmetic sequence, what are we doing? We are adding. Okay, so we're talking about what we're adding. But in your mind, you can think of this, if we're adding a negative value, you can think of this as subtraction. But when writing your common difference, write your common difference in terms of addition. What are we adding? Don't write we're subtracting +3. Rather, we're adding what? Adding -3. So the common difference is what is being added. Again, I'm going to write that. What is being added? Okay, so if you say, well, we're subtracting 3, then write we're adding what? We're adding -3. Now, again, we're going down, going to the right. So you can think of going to the right as subtracting 3. Okay, so if we're subtracting 3 to go to the right, or adding -3 to be proper, let's just use the word subtraction just to help us. Okay, if we're subtracting 3 to go to the right, what are we going to do to go backwards? To go to the left, we're going to do what? The opposite. To go backwards would be to do what? Add 3. Okay, so if we're subtracting 3 to go to the right, we're going to add 3 to go backwards. Why do we have to go backwards? Because you must know the height at 1. Let's go backwards. A sub 8, A sub 7, go ahead and write all these. A sub 6, or height at 6. Height at 5, height at 4, height at 3, height at 2, and height at 1. So we're going to go all the way backwards to height at 1. So let's just keep adding 3 until we get back to the height at 1. 45 plus 3 is 48. Then 51, 54, 57, 60, 63, 66, and 69. Why do we need to know A sub 1? Well, it's not A sub 1 that's so important. Other than to graph. Okay, so for one reason, you need to know the first 4 values in the range, 69, 66, 63, and 60, so that you can graph the sequence. You're always required to graph the first 4 for any quizzes or the test. But also, we want to know that imaginary term that doesn't exist. A sub what? A sub 0, the question mark. This term that doesn't even act as part of the function, this imaginary, what we call the imaginary y-intercept. I'm going to label that again. This is all from introduced in previous videos. Imaginary y-intercept, or the value that doesn't even exist as part of the function. This is going to save us a lot of time because we're going to use this to write the equation of the sequence and move forward. From now on in this class, you can just find the imaginary y-intercept, or if there were a height at 0, to find the equation of the sequence. Now, let's move forward very quickly. We're going to, step one is either to find the common difference, or if the common difference is given, then to work backwards until you find the height at 1. Okay? So, either find common difference or work backwards to find height at 1, reminding you If you had to find common difference, remember common difference is found by taking any two terms and subtracting. So we can take the second term, subtract the first. So to find common difference, you could have taken second, subtract first. 66 minus 69 gives negative 3. Or you could take the third and subtract the second. Okay, 63 minus 66. Okay, 63 minus 66. Any of these will give what? Negative 3. So any two terms, take the second term, subtract the first term. This will give common difference if you had to find it. Now, so now we found the height at 1. We're interested in what this imaginary y-intercept would be. So to go backwards one more value, from 69 backwards was what? 3 more up would be 72. Okay, let's circle this, cross it out. We understand that the imaginary y-intercept is a height of 72. Now, step two is to graph. Okay, we're going to make a t-table again. T-table is in terms of what? N for x. We're not using x and y. N and a sub n. Input is called domain. And the domain is the set of what? Natural numbers. 1, 2, 3, 4, and this goes on forever. So put dot, dot, dot in your t-table. And your range. Your range is the list of values up top. Circle these. Okay, circle these heights and write range. Okay, so 69, 66, 63. Let's go ahead and write our range. 69, 66, 63, and 60, dot, dot, dot. This also goes on forever. We use the dot, dot, dot instead of putting an arrow on the graph. Now, graph the function. We have our n-axis. We have a sub n. Oh, our height at n. Okay. Remember that the units for the n-axis will never change. They will always be units of 1. Why? Because the domain is the set of natural numbers. 1, 2, 3, 4, etc., etc. So you can always leave your n-axis in units of 1. I told you guys to make your vertical axis or your y-axis or a sub n-axis in same units as the common difference or the absolute value of the common difference. In this case, we have a common difference of negative 3, so we're going to make our units 3, 6, 9. Don't write this. Don't write this. I'm going to ask you to erase it. 3, 6, 9, 12, 15. We immediately see a problem. How are you going to graph the point 169 with a reasonable amount of space? Well, if you go 3, 6, 9, 12, 15, 18, 21, how far are you going to have to go until you get to 69? A long ways. Okay, so if you're working with a limited amount of space, especially on the test, I'm going to give you a small graph, maybe a 10 by 10. How are you going to fit the point 169 on your graph? Well, let me show you a trick. Okay, the trick is this. You can change the origin. Instead of the origin being 0, 0, you can change its location to any location you want it to be, as long as you label it. So instead of 0, 0, how about we change the origin? I'm just going to give you an example. How about we change the origin to 0, 60? Okay, this means that the y values start at 60 or the heights start at 60. Okay, and now do units of 3 for your common difference. So we have 60 is the first height. The next height would be what? 63, then 66, 69, 72, 75. And my question is, what are the values in the negative direction? Be careful here. Okay, if this is 63 height, and this is a height of 60, notice y value, or height at 60, we put the 60 for the y value. What is the height below, the first height below the n-axis? Okay, so we're looking at a height of what? 3 less than 60, or 57, then what, 54? So I require this. If you change the location of the origin to, say, 0, 60, then you need to label both your positive and your negative scale. Okay, so I need to see the negative direction as well, so I understand that I see that you understand that the units continue in this direction. Even though we're below the n-axis, the values are still positive. Okay, so 57, 54, 51, 48, and etc., etc. Now, let's go ahead and graph the first 4 values. We have 169, it's here, okay, and then 266, 363, and 460. Remember, we call this a linear pattern. A linear pattern, but do these points form a line? Absolutely not. These points do not form a line. Why? Because the domain is just the set of natural numbers 1, 2, 3, 4, and there are gaps. There are no points at 2.5. Okay, so at 2.5, there is not a point. Okay, so at 2.5, for instance, 2.5, 2.5, 64.5. 2.5, 64.5 is not a value in our function. 2.5 is not a domain value, so at 2.5, 64.5, we do not have a point. Okay, there is no point here. I'm going to erase this. Okay, so we have gaps between our points. Okay, we do not connect the points because connecting the points is like graphing infinitely many points between any 2 points. So we're not connecting the points. Okay, there's a big gap between any 2 points. All right. Okay, so we talked about this again in previous videos. Now, instead of putting an arrow on the graph, we use the dot, dot, dot in the t-table. Okay, these points go on in a pattern forever. Okay, we call this a linear pattern. We use a linear function to study this. Now, is there a y-intercept, or is there a point that lies on the y-axis? No, because 0, again, is not in the domain of the function. But if we look at this imaginary y-intercept, this a sub 0, 72, go ahead and put 0, 72 in your t-table again, cross it out. It's not actually part of the function. Why? Because 0 is not in the domain of natural numbers. And we put 0, 72 as here. Okay? So I want you to put an open circle. Open circle means it's not even there. There's nothing there. There's no point. Put an open circle to indicate, would this be the location of the imaginary y-intercept? Yes, you can label this the imaginary, okay, imaginary y-intercept. It's not actually part of the function. Okay, it's just, if there were a y-intercept, it would occur right there in that open circle. But there is no point there. Okay, so that's why we put an open circle. That's better. Now, instead of going through the steps, step 3 was to find the equation. Instead of going through the steps of the equation where I gave you a sub n minus a sub k equals d times quantity n minus k, let's go ahead and just use the trick. Today, just use the trick. Okay, so from now on, actually, in this class, use this trick. The imaginary y-intercept would be at 0, 72. So I want you to write, again, this is related to what? Linear function. So I want you to write y equals mx plus b on your paper. And instead of y, what variable are we using? We're using what? A sub n. So a sub n equals, and slope. What is the same concept as slope? Remember, common difference is the same. We can use this as, or think of this as the same thing as slope. Okay, so instead of slope, we're looking at common difference of what? -3, so we have -3, and instead of x, we're using variable what? Variable n, so -3n, and our imaginary y-intercept. Imaginary y-intercept is at 0, 72, so we're going to use the b value of what? The imaginary value of what? 72, so plus 72, and this is the equation of the sequence. Okay, so instead of going through the form, the point-slope form that we looked at, we're going to use what? The trick. Using the imaginary y-intercept, you can quickly write the equation of the sequence. The equation is a sub n. Let's see, get it darker so you guys can see it on the camera. A sub n equals -3n plus 72. Okay, now, step 4 is to find the height at what? Height at 50. Okay, and this is represented by a sub 50, or symbol, I should say, a sub 50 represents height 50. Now, underneath the equation, you can write a sub, here, I'll write the equation again, a sub n equals -3n plus 72. We're going to find the height at 50, so you write a sub, what, 50? Okay, so what's replacing n? What is replacing n? 50 is replacing n. So we're going to replace n with 50 here. We get -3 times what? -3 times 50 plus 72. This is -150 plus 72 gives -78. Okay, -78. -150 plus 72 is -78. That is correct. All right, now, so we have height at 50 equals -78. And again, this is much more efficient than going forward. Notice height at 5 is 57, height at 6 is 54, height at 7 is 51, height at 8 is 48. And going through this pattern all the way to the 50th height would take a long time, but rather just using this quick this formula. What is this equation good for? This equation is good for generating large heights. Now, so height at 50 is -78. Step 5, here. Step 5 was to write, I'm going to erase this. Step 5 dealt with series. Okay, so step 5 was series. Okay, completely different than what? Completely different than sequence. Remember, the series is a sum of the set of range elements of a sequence. And so I told you in step 5 to find the sum of the first 10 elements of the range. Remembering that sigma means add, okay? And what are we adding? We're adding the range. Remember that the symbol a sub n represents range, but we need to be more specific. Okay, so a sub n is what? Symbol for range. What is more specific? A sub n is very general. A sub n represents range of any sequence. Any sequence. But what specifically represents this range? What is the name of this range? Okay, so a sub n is range, but we have the name. Remember, range is equal to what? Range is equal to range. Okay, so range is equal to range, and in this case we have the name, the specific name of this range. We found it in the equation. That range is what? Negative 3n plus 72. This is the name of this range. So I want you up here next to range, I want you to write negative 3n plus 72. This is the name of the range that you're looking at, the range of this circle, okay, the heights. Now, so instead of writing sigma a sub n, we're going to be more specific and write sigma what? Sigma negative 3n plus 72. And again, we're adding what? The first 10 elements. We read this as add the range. Okay, I'm going to write the add down here. Okay, add the range. And we're adding what? The first 10 elements, and we read elements as numbers. So we say from n equals what? 1 to 10. The first 10 numbers of the range. This is our domain. Okay, domain goes from 1 to 10. Okay, so we're looking at domain 1, 2, 3, 4, position 1, 2, 3, 4, position 5, position 6, position 7, position 8, position 9, and position 10. And now we're looking at what are those range values in these positions from 1 to 10. The range values in those positions are what? Well, we see the range values here. 69, so we write 69, 66, 63, 60, 57, 54, 51, 48, 45, and 42. And remember, sigma means add, so we're adding these values up. Let's put addition. Okay. And there's a quick trick here. There's a quick trick. Let's see. I think it's 555. Let's see. Yeah, 555. Okay, so quick trick. Have you figured out the trick to adding these values very quickly? You don't actually have to add them up in your head. Remember, the Einstein trick that he was asked to add the numbers from 1 to 100 turns around and goes, well, the sum of all numbers from 1 to 100 is what? 5,050. Okay, he figures this out in his head. Now, it's a rumor. I don't know if this is actually true or not, but it's fun to think that Einstein was asked this question and turns around and goes, yes, the sum of all numbers from 1 to 100 is 5,050. Okay, but I believe there is a case of some famous mathematician who did figure this out as a child. Now, and these questions are asked. These questions are asked in competition elementary math problems. Okay, so add all the numbers from 1 to 100. Go. Okay, you've got 3 minutes. Go. Now, let's see. Yeah. 555. Now, we also have to look at how to read the sigma notation. So looking at here. What if I give you the problem sigma n equals 1 to 10 of negative 3n plus 72? And this was problem number 3 on a quiz. Okay, how do you deal with this problem if you're just given this problem without knowing this information? Okay, so you don't know what your range is. All you're given is this problem. Without knowing any information over here, can you read this problem? Okay, remember, this is a stepladder. N goes from 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're putting in what? We're putting in 1 for n. We're putting in 2 for n. We're putting in 3 for n. Okay, so we're going to calculate the first 3 and see if we can find a pattern. So we write negative 3 times 1 plus 72. We're putting in 1 for n. Negative 3 times 2 plus 72. Negative 3 times 3 plus 72. Okay, so we put in 1 for n. We put in 2 for n. And we put in 3 for n. Let's see if we can find a pattern. Okay, and obviously this is going to be the numbers that we've already written up, that are already on the board over here. But again, you won't know this information. So can you read this question? Negative 3 plus 72 is 69. Negative 6 plus 72 is 66. And negative 9 plus 72 is 63. Now, 69, 66, 63. So we write this is equal to 69, 66, 63. And remember, what does sigma mean? Sigma means what? Add. So we're going to put addition, not commas. So 69 plus 66 plus 63 plus, what's the next value? Well, we see a pattern here. What's happening to the values? The values are going what? The values are going down by 3. So the next value will be what? 60 plus what? 57. Keep going down by 3 plus what? 54 plus what? 51. Now hold on. We need to know where we're stopping. Now to know where you're stopping, you put in what? You put in the last domain value. You put in 10 for n. So negative 3 times 10. We're going to calculate. Putting in 10 for n, negative 3 times 10 plus 72 is negative 30 plus 72, which is 42. So we're stopping when we get to 42. Now, so keep going. 51 plus 48 plus 45 plus 42. And now you can simply count to make sure there are, what? How many numbers from 1 to 10? There are 10, okay? So we said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, this is all of them. And we get 555. All right, so the sum of these numbers is 555. See if you can figure out this trick. Now, going to the next topic. Okay, so this was arithmetic series, or I'm sorry, arithmetic sequence with a short introduction to arithmetic series. Now, there will be a video devoted primarily to just series, okay? Okay, so how to read this, all right, but not yet. We're still focusing primarily on sequence. All right, now, next sequence, all right, same thing. The definition of a sequence does not change, but we're not looking at arithmetic sequence now. We're looking at a new topic. Okay, this topic is geometric sequences. Okay, now arithmetic sequence meant something is being added. Geometric sequence will mean something is being multiplied. Okay, something is being multiplied. Something is being multiplied. And we will be on page, not 692, we'll be looking at page 700. Okay, page 700 now. Erase this off the board. I'm going to give you an example. The first geometric sequence we're going to look at is something very simple. It's the same steps, so there's not a big learning curve for this because you've already done arithmetic. But we're going to start with something very basic. So we're looking at the sequence, let's say 4, 8, 16, 32, dot, dot, dot. Okay, dot, 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 meaning, again, it goes on forever. Okay? Now, arithmetic meant something is being added. Geometric means something is being multiplied. Now, with arithmetic, we called what's being added the common difference. Okay? Now, geometric sequence does not have a common difference. We call this, instead, we call it a common ratio. Okay? Common ratio. And common ratio means what is being multiplied. Okay? What is being multiplied. Okay, what is being multiplied? This is denoted by variable r. Okay, and to find the common ratio of what is being multiplied, so your first step tonight is to find what? First step is to find common ratio or what is being multiplied. We use variable r. Now, with arithmetic sequence, for instance, I'm just going to put one up here. 5, 10, 15, 20. To find what was being added, the common difference was found by taking the second value, 10, and subtracting the first value, 5. So to find what was being added, we subtracted. To find what was being added, notice 5 is being added, 5 is being added. Okay, so to find what's being added, we subtract. Okay, so to find what's being multiplied, what are we going to do? To find what's being multiplied, you can look at this and tell me, what are we multiplying by to get from 4 to 8? We're multiplying by 2. To get from 8 to 16, we're multiplying by 2. To get from 16 to 32, we're multiplying by 2. So you can tell me that we're multiplying by what? Multiplying by 2. But more so than arithmetic, I said that the common difference in arithmetic is not always easy to find. So we subtract. It's not always obvious, so we subtract to find it. We take the second term, subtract the first. Or you can take any term. You can take the third term and subtract the second. 15 minus 10. Any two adjacent terms will find the common difference if you subtract. So to find what's being added, we subtract. But it's not always obvious what's being added. But more so than this, in the geometric sequence, it's very more often than not, it's very hard to find common ratio, or it's not obvious when you look at it what the common ratio is. So you need to know, to find common ratio, we're going to take the second term, which is 8, and divide. Okay, so if we try to find what's being added, we subtract. To find what's being multiplied, we're going to do what? Divide. So take the second term, 8, and divide by what? 4. So 8 divided by 4 gives 2, or our common ratio is what? 2. All that to say, divide to find what's being multiplied. Now you don't have to take the second and divide the first. You can also take the third and divide the second. You can also say common ratio is 16 divided by what? 16 divided by 8 also gives 2. Or you can say common ratio is 32 divided by 16. 32 divided by 16, the fourth minus the third, is also 2. Okay, so we get common ratio any two terms as long as you take the second term and divide the first. Now, okay, I'm going to erase this and rewrite it. So we have 4, 8, 16, 32, dot, dot, dot. Now, dot, 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 meaning it goes on forever. Underneath this, write a sub 1, a sub 2, a sub 3, a sub 4. Remembering that a sub 4 means what? Height at 4, and the height at 4 is 32. Circle this. This is called our range. And just like we did with arithmetic, we're going to graph it. So step 2 will be to graph. We need a t-table. Okay. In terms of n and a sub n, remember our domain does not change no matter what sequence we're dealing with. The domain is what? A set of natural numbers. It says a sequence is a function whose domain is a set of what? Natural numbers. So we write 1, 2, 3, 4. Again, we're going to have gaps, but dot, dot, dot. Gaps in our points. We are not going to connect our points. And the range. Okay, so the range will be the values circled. In this case, 4, 8, 16, 32. Are there more values? Yes, they go on forever. But dot, dot, dot. And we're going to graph this. Okay, now, the n-axis will never change. So n-axis is in scale, scale of 1. And the y-axis. With arithmetic, I told you guys to make your vertical axis scale the same as your common difference. With geometric, there's no trick. You just have to figure out a scale that will work. Now we have 1, 2, 3, 4, 5 spaces to fit 32. So I always divide. Can we do 32 divided by 5? No. Okay, but if we go down to 4 spaces, can we do 32 divided by 4? Yes, we can divide 32 into 4 equal parts. And so we're going to have what? 32 divided by 4 gives 8. So we get 8, 16, 24, 32, and 40. Don't make this mistake. I see a lot of students do this. Okay, don't make this mistake. I see students, after dealing with geometric, they try to make a scale like this. They try to make a scale 8, 16, 32, 64. What's happening in the scale? Okay, this is not, okay, we don't make a vertical scale geometric in nature or something's being multiplied to get to the next term. Notice, multiply by 2, multiply by 2, multiply by 2. No, the vertical scale cannot be geometric in nature. Okay, we're not multiplying to get to the next value. Okay, the vertical scale has to be arithmetic in nature, or something is being added to get to the next height. So you cannot do this, 8, 16, 32, 64. No, 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 no. This is wrong. No, your vertical scale has to be arithmetic in nature. Okay, so 8, what's 8 more? 16, what's 8 more? So add 8, add 8, add 8. What is this? 24. What is this? 32, and what is this? 40. So your vertical scale always has to be arithmetic in nature. Students get confused when they start studying geometric sequences and think that they can make their scale geometric in nature. No, the scale has to be arithmetic. Now, down here we have what? Assumed to be negative 8, negative 16, etc. Now, let's graph the points. We have 1, 4. Okay. We have 2, 8, 3, 16, and 4, 32. Now my question is, this looks a lot like a function we've studied. Remember when we studied arithmetic, it reminded us of linear function, and we used linear function to study, or concepts we'd learned with linear function to study arithmetic sequence. Now this is a geometric sequence, but does this look like, notice it has curvature to it, does this look like a function on our parent functions list? Yes, it does. Now many students guessed quadratic, but it's not actually quadratic. I will show you. It is actually related to the exponential function. Remember, the exponential function has this shape, okay? Takes off very quickly, gets forever close to what? Gets forever close to the x-axis, but never touches. Okay, this is exponential function. And remember, the equations of the exponential function are y equals a times b to the x power, or y equals a times e to the x power. And I want you to notice something. Notice that x is acting, our x-axis in the equation, the exponential equation, x is acting as the exponent. Okay, so this is going to help us be familiar with, and in fact, the geometric equation for this sequence is going to look very similar to this. Okay, notice that for an exponential function, the x-axis, variable x, is acting as the exponent in the equation. Okay, so notice x-axis is the same as exponent. Now, step 3 is to write the equation of this sequence. Now, with arithmetic sequence, you guys needed to know a sub 0 or height at 0. The imaginary height that didn't actually exist as part of the function. For geometric sequence, this is different. You need to know height at 1. Okay, so we're not interested in finding height at 0 or the imaginary height at 0. For geometric sequence, you need to know what? Height at 1. Okay, so height at 1 here is 4. I'll show you why. The equation is a sub n, and this is just memorized, a sub n equals a sub 1 times r to the n minus 1 power. Okay, so we have a sub 1 equals r to the n minus 1 power. Now, r is the common ratio. Okay, r is the common ratio. We already found this to be 2. And a sub 1 is our height at 1. Height at 1 is what? 4. So we're going to write the equation very easily here in a moment. Now I want you to notice what axis, instead of x-axis, what do we have here? Instead of x-axis, we have what? N-axis. Notice in the exponential function, x-axis was acting as exponent. With geometric sequence, the n-axis is acting as what? N is acting as the exponent. In this case, we have n minus 1, slightly different, but very similar. Okay, so n-axis is acting as what? N-axis is acting as exponent. Now, to write the equation is very simple. A sub n is y equals, and we need a sub 1. Okay, so height at 1 is what? Height at 1 is 4. This is actually very, very easy to write. 4 times r value is what? R value is 2. So we say 4 times 2 to the n minus 1, and you're done. You have written the equation. You have written the equation of this geometric sequence. Okay, so the equation is a sub n equals 4 times 2 to the n minus 1 power. All right? Now, step 3 was equation. Step 4 is to find, if I asked you to find height at 50, just to give you perspective here, the height at 50, height at 1 is 4, height at 2 is 8, height at 3 is 16, at 4 we have 32, at 5 we have 64, at 6 we have 128, at 7 we have 256. Notice that the heights are taking off. The heights are taking off extremely fast. At 50, the height is literally more than a trillion. It is so huge. Okay, it's like a trillion times a trillion times a trillion. It is so huge it will blow your mind. So I'm not asking you guys to find height at 50. These heights get huge very, very quickly. By the time you get to the 20th height, you're already in the millions. Okay, so you're huge by the time you get to the 20th height. They're very close to millions at that point. Okay, so height at, let's just say height at 5 for geometric. So I want you guys to find height at 5. What I want you to be used to is, I want you guys to be able to use this equation. Students say, well, I can tell you what the height at 5 is. The height at 5 is what? To go one more value, is height at 5 would be 64. You can look at this and tell me what the height at 5 is, but I must make this clear. On the SOL, you will not know this. Okay, you will not know these values. In fact, you will be given just an equation and asked to find a specific height, a height at 5. For instance, okay, so can you use the equation to find height at 5 without knowing any of this information? Okay, so I'm going to show you. To use the equation, let's write a sub n equals a sub 1, the equation specifically is 4 times 2 to the n minus 1 power. Okay, and we're going to find what? Height at 5. So we're finding a sub 5. And notice, what is replacing n? What is replacing n? Well, hopefully you say 5 is replacing n. So we're going to have 4 times 2 to to the 5 minus 1 power. Now my question is, do we multiply the 4 times the 2? No. Okay, do we multiply 4 times 2? No. This is done last. Let me remind you guys of the acronym. You guys remember, please excuse my dear Aunt Sally. In this class we use please excuse my aunt. Now what comes first? What comes first? Parentheses come first. So what is to be done? We check parentheses first. What is to be done inside the parentheses? Is there anything that needs to be done inside the parentheses? No. So we're done with parentheses. And now we switch to what? Exponent. So what has to be done next? The exponent. Okay, so we're going to take 2 to some power. But before we do this, let's fix the exponent. It says 5 minus 1. Let's cross that out. What is 5 minus 1? 5 minus 1 is 4. So cross out the 5 minus 1, put 4. And now let's do the exponent. So we're doing 2 to the 4th power. 2 to the 4th power is not 8. 2 to the 4th power means what? It means 2 times 2 times 2 times 2. Okay? 2 times 2 is what? 2 times 2 is 4. Okay? Times another 2 is 8. Times another 2 is what? 16. Okay? Another way to do this, multiply 2 times 2 and get 4. Multiply 2 times 2 and get 4. Now multiply your 4's together. 4 times 4 is what? 16. So 2 to the 4th power is 16, so we end up with a sub 5, or height at 5, is 4 in front, times the 2 to the 4th power became 16, and we get what? 4 times 16 is 64. So we end up with height at 5. Height at 5 is equal to what? 64. Okay? Now, lastly, you need to find the sum. Now, I'm not going to ask you guys to find the sum of the first 10, since these heights get large very, very quickly. But instead, step 5, you guys will find the height of the first 5 terms. Okay, so step 5, find height. No, not find height. Find the sum. Okay, find the sum of the first 5 elements. So for geometric, just 5. 5 elements of the range. Okay, the first 5 elements of the range. Now, again, we call this when we're adding. So basically, what are we doing? We are adding the range values together. Okay, so we're adding these range values 4, 8, 16, 32. We're adding these up. And remember, this is called what? Series. Series is a separate topic from sequence. It's different. Okay, so we're adding. Remember, sigma means add, and we're adding what? Adding the range. So right, add the range. Remember, a sub n represents what? Range, but we want to be more specific. Okay, so same thing we did with arithmetic. Remember that a sub n, going back to the equation. All right. Remember that a sub n represents what? A sub n represents range. And also we remember that range is equal to what? Range is equal to range, but we want a specific name for this range. A sub n is too general. We want a specific name for this range. A sub n is general, a sub n is arithmetic, a sub n is geometric. What range are we talking about? The 4 times 2 to the n minus power is the name. This is the specific name of the range that we're dealing with. So up here next to the range, I want you guys to write, what is the name of this range? The name of this range is 4 times 2 to the n minus 1 power. Okay, so I want you to write the specific name. Okay, so instead of sigma a sub n, we're writing what? We're writing sigma. And the specific name of the range is 4 times 2 to the n minus 1 power. And we're adding what? The first 5 elements. Remember, this element means number. So the first 5 numbers in the range. So we say from n equals 1 to 5. Remember, this is your domain. Okay, this is your domain. Sigma means what? Sigma means add. And this is what? Range. Okay, so we're adding the range. And what numbers in the range? Well, we're adding the first 5 elements of the range. Now we just copy them down. What are they? Well, we have 4. Add what? Add 8 with their elements in the range. Add what? Add 16 plus what? Plus 32. And I think you guys can figure out the 5th. Well, we did calculate the 5th over here, yes. Is what? 64. And now, for the arithmetic sequence, I told you that there was, for arithmetic series, I told you there was a trick for adding these values. For geometric, there is no trick. Geometric, there is no trick. Now, I haven't even shown you what the trick is yet. If you've tried to, maybe figure it out, but there is no trick for geometric, so you just simply have to add these up. 64 plus 32 is 96, plus 16 is 112, plus 8 is 120, plus 4 is 124. So we get a sum of 124. You just simply have to add these numbers up. Now, before we conclude this video, you also have to be able to read soon. Okay? And again, series, the topic of series will be covered in its own video, but I'm trying to get you guys ready for this and try to relate it to sequence itself. Okay? Now, you have to also be able to read this expression, okay, or this series, sigma n equals 1 to 5, since it's written on the board over there, but act like we don't know anything on the board. Let's act like we don't know any of this, okay? So given a problem on a quiz or a test, okay, sigma n equals 1 to 5 of 4 times 2 to the n minus 1 power, okay, can you find this value or this sum? Act like this is question number 3 on a quiz or a test. Now, well, what do you have to do? Well, you have to plug in, remember this is a step ladder, you have to plug in 1 for n, 2 for n, 3 for n, 4 for n, and what else? 5 for n. So we have to plug in 1, 2, 3, 4, 5. We have to plug in all these values for n. So let's write it out. We have 4 times what? 4 times 2 to the 1 minus 1, plugging 1 in for n. 4 times 2 to the, putting in 2 for n, 2 minus 1. 4 times 2 to the 3 minus 1. 4 times 2 to the 4 minus 1. And 4 times 2 to the 5 minus 1. So what are we plugging in? We're plugging in 1 for n. We're plugging in 2 for n. We're plugging in 3 for n. We're plugging in 4 for n. Okay, and we're plugging in 5 for n. Okay, now, let's calculate these values. Let's cross this out. Remember, please, excuse my aunt says, what do we do first? We do parentheses first. Well, if we look inside the parentheses, is there anything to be done inside the parentheses? No. So we're done with the parentheses. We switch directly to exponent. Let's cross the 1 minus 1 out. What is 1 minus 1? Well, that is 0. Okay? Now, cross out the 2 minus 1. 2 minus 1 is 1. Cross out the 3 minus 1, we get what? 2. Cross out the 4 minus 1, we get 3. And cross out the 5 minus 1, we get 4. So our exponents are 0, 1, 2, 3, and 4. Now we're going to calculate each one of these values, starting with the exponent first. Before we do 0 power, I need you guys to know this. Okay, so question, what is 7 to the 0 power? 7 to the 0 power is 1. Okay, anything to the 0 power, watch. 8 to the 0 power is what? 1. 9 to the 0 power is 1. Negative 153 to the 0 power is 1. 596.3 to the 0 power is 1. Negative 1,273.26 to the 0 power is 1. So we see anything to the 0 power. Anything to the 0 power is 1, right? Okay, question. What is 0 to the 0th? What is 0 to the 0th? No, it's not 1. 0 to the 0th is what? 0 to the 0th is indeterminate. This is going to be huge for what's coming in this class. Indeterminate. Okay, so 0 to the 0th is indeterminate. So anything to the 0 power is 1 except what? Except for 0. 0 to the 0th is indeterminate. Now going back to this. So we have 4 times 2 to the 0. We do our exponent first. So we're looking at 2 to the 0 power. So my question is, what is 2 to the 0? Well, 2 to the 0 power is 1. So we end up with 4 times 1, which is what? 4. Okay? And now next, we do exponent. 2 to the first. Okay, so 2 to the first power here. 7 to the first is what? 7. 8 to the first is what? 8. What is 2 to the first? 2 to the first is 2, so we end up with 4 times 2, which is 8. And now we do 2 squared. Okay, so now we're looking at 2 squared. 2 squared does not mean 2, 2 squared means 2 times itself. So we're looking at 2 times 2, which is what? 4. So 2 squared is 4. We end up with what? 4 times 4, which is what? 16. Okay, now, we're doing 2 to the third. 2 to the third is not 6. 2 to the third means 2 times 2 times 2, or 2 times itself 3 times. 2 times 2 is 4, times another 2 is 8. So 2 to the third is what? 8. So we end up with what? 4 times 8, which is 32. And lastly, 2 to the fourth power. 2 to the fourth power means, I'm going to erase all this, and we're running out of space here. Okay, 2 to the fourth power means what? 2 times 2 times 2 times 2. 2 times 2 is 4, times another 2 is 8, times another 2 is 16. So we end up with 4 times what? 16, which is what? 64. So we have the values 4, 8, 16, 32, and 64. And I want you to notice, although we don't know this information for this problem, since this is written on the board over there, can we compare 4, 8, 16, 32, 64, 4, 8, 16, 32, 64. Even though, again, we don't know this information when doing the problem, for now you can look and compare. You see it. Okay, so what are we adding here? These are the values in the range, 4, 8, 16, 32, and what? 64. So what are we adding up here? Remember, sigma means add. We're adding what? 4 plus 8 plus 16 plus 32 plus 64. And if you guys want a trick to help you add this, one trick is to simply add numbers that make multiples of 10. So if we look at 16 plus 4, what is 16 plus 4? Well, that's 20. Cross that out. Now look at 8 plus 32. 8 plus 32 is what? 40. Okay, cross those out. Now you can simply add 20 plus 40 is what? 60 plus 64 gives 124. Okay, so that's a trick to simply adding those quickly. All right, that concludes this video. Hopefully you've got an idea, or at least an introduction to geometric sequence. Geometric sequence means something is being what? Something is being multiplied, and we call this a common ratio denoted by variable r. And remember that the common ratio is found by taking the second value and subtracting what? I'm sorry, not subtracting. Taking the second value and dividing the first. So in this case, 8 divided by 4 gave what? A common ratio of 2. Okay, so common ratio instead of common difference. All right, great.